Hi there, folks, this is Aaron Harper. It is currently 8 o'clock and I am now ready to confirm the findings of Robert Murray Smith regarding the process, a simplified process by which graphene can be extracted from graphite. In his experiment, he used a piece of graphene foil, probably only microns thick. What I had available was graphene foil 1/32 of an inch thick, designed for gaskets and high temperature applications. The process, other than that, will be followed fairly closely, and the next step is to show the apparatus. Okay, the apparatus is, just 1 second, I'm used to operating this camcorder with my gloves on. Yay. Okay, the apparatus, as you see, is a 24 volt power supply, which in turn feeds the ammeter, which is connected to the ground return side, and to 2 voltmeters. And these voltmeters are also power supply modules. You'll see the first is set to 2 volts and the second to 10 to replicate Robert's methods, where he used 2 volts for approximately 30 seconds and then 10 volts for the remainder of the cycle. We'll also be monitoring the current in the ammeter and the voltage in the voltmeter. All connections are a rat's nest. I apologize for that, but this is a proof of concept. Time will be kept on this timer. We'll be using that to mark off the 30-second I guess charging or loading of the ions into the graphene to exfoliate. Rather than use a switch, this is the common wire which connects to the positive lead here. The ground lead goes back to the ammeter, if it will focus. The ammeter here, which in turn goes back to the ground return. We'll give it some more light, it probably will focus then. Or not. Alright. Here you see the these are marked with the voltage. This one 2 volt, this one 10. And if I want to put 2 volts on, I will connect these two. And if I want to put 10 volts on, I disconnect the 2 volt and connect the 10 volt. This simulates basically a relay operation for the industrial process. The next step will be to take the piece of graphite, which you see here, and as I said, the main difference is it is actually quite thick. It's designed for high temperature motorsport and aerospace applications. It's what I had. And for the positive, the anode, I'm going to use this piece of stainless steel. The 2 clamps here, the 2 clips, these are not used for electrical work, but rather to clamp the electrodes to the side of the glass, so that there won't be an inadvertent short. The next step will be to create the 5 molar sodium sulfide solution, which I won't cover. It's fairly straightforward, but requires 2 hands. So with that, we'll cut to the start of the actual experiment, where we will adjust the camera angle to make sure that you can see the voltmeter, the ammeter, and the experiment going on. You most likely will not be able to see the voltmeter, although the voltmeter on the power supplies are fairly close. Alright, I believe that 5 molar may be a little bit of a overstatement, since it seems to be beyond the saturation point. This is the results of 2 experiments trying to develop, trying to put a solution of 5 molar sodium sulfate together, and it's not a lot. What resulted, however, is this is just shy of a saturated solution, and should be somewhere in the neighborhood of 1 to 1.2 molar, and we're going to go ahead and give that a shot for our experiment. So bear with me, and we will set up the camera to record. Alright folks, there's our experiment. We have the piece of stainless here and the piece of graphite here, which is both are being held by these large alligator clips, and these leads go back to our power supply at that point, reading through our ammeter, and we will find out what kind of voltage it's actually putting out, although you won't be able to see that when I put the camera down. Everything's going to be timed using this timer and switched using those as we discussed earlier. Again, this is a saturated solution of the electrolyte, and we will see exactly what we get out of it. It's of unknown molar concentration, and we will be playing around with that a little bit more as time goes on. There, that way we can see what's going on. Alright, setting the timer. For 30 seconds. And we are now going to connect to 2 volts. Oops, come on, stand up. Connecting to 2 volts now. As you can see, the current is going through the electrolyte. Oddly enough, it is reducing. I'm not entirely sure what that's all about. And I'm not seeing anything that looks like gasification at this point. So now we are going to connect to our 10 volt supply. And we see the effect that Robert was talking about. It's rather vigorous, I might add. I'm also pulling 2.7 amps. So this was obviously a much stronger concentration than he originally had in mind. This is a little beyond the rating of the power supply module, so we might see a cutout at some point. Our graphene nanoplatelets raft at the top continues to grow. I'm going to go ahead and show you that. And this apparently is what we're after. Find it interesting exactly how much of a vigorous reaction we're also seeing off of the stainless. The raft is actually approaching the other electrode, and the current does not seem to be going up. So I'm going to go ahead and let it do its thing. The vigorous reaction on the stainless is providing somewhat of a guard, but it will be making contact very shortly. In fact, it already has made contact, but the current does not seem to be affected at this point. There isn't really a disagreeable smell. There's obviously something going on, but it's not an overly strong smell. I actually have to try to smell. And there's no catch at the back of the throat. That would seem to indicate a gas of some sort that is a problem. We have dropped down to 2.6 amps. The nanoplatelet raft is in direct contact with the other electrode, and the erosion of the graphite is continuing very vigorously. Okay, the conductivity seems to be going up. I'm going to remove some of the material from the raft and push it over against the other electrode. That seems to have brought the current down, and the raft itself is quite conductive when it ends up being a fairly substantial amount of material. At this point in time, I'm going to unpin the graphite, and I'm going to go ahead and submerge the remainder. And pull the material from the raft away from the other electrode. I believe it may be a good idea to wrap the top of the electrode in some sort of insulator. Could be something as simple as electrical tape or Teflon to prevent the raft from making contact. As you can see, the material continues to decompose quite vigorously. At this point in time, I'm going to get another vessel and decant some of the raft from the top. Alright. Alright, that seems to have brought down the current a touch. And the material seems to be something that could be filtered relatively easily. Alright, I'm going to attach the electrode on the side via the clip to continue the process. I'm going to continue to grab the material. That appears to be a chunk of the material of the original electrode, so I'm going to set it aside. And that's my meter telling me it's time to turn it off. It would appear as the salt becomes expended, the current is dropping, though the growth of the raft toward the other electrode seems to have the opposite effect. My meter has now turned off. The material is continuing to go quite cheerfully, which tells me we have plenty of the sulfur intercalating the graphene or the graphite. I'm going to move the electrode toward the camera. And I'm continuing to decant the resultant material. This is rather impressive, the amount of yield. as you can see, the material is continuing to erode and is almost complete. I find it interesting that the electrolyte seems to have taken on almost a brownish hue. Not sure what that's about. I was certainly not expecting this level of production. I also get the feeling that my other electrode, which I assumed was stainless steel, is not. There seems to be a discoloration. Doesn't seem to be affecting anything, however. Seems to be rather cheerfully reacting away. Check on our piece of graphite. Well, at this point in time, I'm going to call the experiment complete. The material in question this is what remains. And I'm turning off the power supply. And we will, in post-production, see exactly how much time that took. I'm going to continue to decant the material. Well, interesting. The material, you can see how the material seems to have been discolored slightly, though not badly. I'm going to assume that it is actually stainless steel. And I'm pulling out the last of the exfoliated graphite. And normally this is where we take what's in here and put it in a wet grinder or sonicator or several other methods to mechanically shear the loosely bounded graphite. Alright, as you can see, the material remains slightly large. There's what's left of the graphite, and it remains on the spoon. There's what remains in the beaker, and looking at the bottom, there's not a whole lot of precipitate, which I would expect, considering that the item that I was using as a test article was basically pure graphite. Now, this is what the resulting material is. And naturally there is quite a bit of a liquid component still. But, you know, just for sake of comparison, there's my hand. And I've yet to dry it and weigh it, but I will report back. I'm also going to try to filter off the remainder just to get an accurate measurement, and the result should be interesting. From what I'm gathering by virtue of the current and the rest and the vigorousness of the reaction, that's all there is.
Thanks for watching.
I get the feeling that what was said being 5 molar was incorrect, and it was probably 0.5 molar, but nonetheless the results are positive. All that means is that we have absolutely plenty of the sodium sulfide. That's the stuff in the envelope or in the plastic bag, plus everything in the graduated cylinder. If I manage to extract that out, that's probably one solid mass, and it will take a bit of effort to get it out. But essentially, that I'm willing to call a success. So, okay, yeah, left a little bit of a mess, but that's what you deal with when you deal with saturated solutions. This is what was left after a rinse, and while it looks rather promising, there are some light spots, and after a little bit of analysis, it became pretty clear that the reaction was vigorous enough to quite literally blow chunks of the graphite clean off the surface, so that it no longer made electrical contact. The reaction is far too vigorous in this configuration. Of course, we kind of knew that, mainly because there you can see a nice chunk of graphite. Mainly because of the concentration, which was obviously incorrect. What I'm going to experiment with next is reduction of the concentration. I'm going to try 0.5 molar next, and should that prove somewhat successful, we'll go ahead and use that. And the other thing that I am going to try is reduce the amount of material in possibly below 0.5 molar in order to utilize a higher voltage. the voltages I'm after using is 3.3 volts and 12 volts, and this is in order to utilize a PC power supply right off the shelf. So more on this later. The bottom line, however, is that this was a success. We have produced the exfoliated graphite in the form of graphite, graphene nanoplatelets, which are in strings, and the next step would obviously be to put it through a some kind of mechanical shear process. Probably the easiest would be a wet grinder, such as is used in some Indian foods to produce a custard out of rice. More on this later. Right now it is way late, and I'm heading for bed. Thanks a bunch.